Hello, class. So in this video, we'll still continue on section 6.3. Right? In the previous video, we saw the importance of step functions. Specifically, we saw how if we have a function g of t in which the c in which we turn on the function matches the shift in the function inside the definition, right? So inside the piecewise definition, then we can write the original function as just the product of the step function with the shifted part inside the piecewise function. So that's what we did in the previous video. And then we saw that we had this really nice theorem of how to compute the Laplace transform of a step function times a shifted function in which the shift, again, matches the c in which we start the function. What we saw is that we get this really nice computation, meaning that we can just take this e to the negative cs on the outside and compute the Laplace transform of the unshifted version of what's inside the piecewise function. And then similarly, we also get a Laplace inverse definition, assuming that your function f is continuous. So we did an example of this. Right, so we went over this example. We saw that this function f satisfies the conditions because the time in which we start the function matches the shift in the function inside the piecewise definition. So we went over all that. Okay? Now, let's do an example of instead given a function of s trying to find the inverse Laplace transform. So find the inverse Laplace transform of 1 minus e to the negative 2s over s squared. First of all, we're going to use the linearity of the inverse Laplace transform. So this is going to be equal to 1 over s squared minus Laplace inverse of e to the negative, e to the negative 2s times 1 over s squared. Right. And again, this is just separating the difference. Again, using the linearity of the Laplace transform. Now, this, we can go back to our table, and you can identify that this is just the Laplace transform of t, right? Which means that this Laplace inverse of 1 over s squared is just t. Now, minus, now let's work this part out. Now, if you look at this here, this looks like, at least this part, looks like a shift by 2 units. Right? And again, that comes from theorem 1, when we calculate this Laplace transform. So, making that notice, we're noticing that, actually let me highlight it so it's easier to read. Right? So noticing that this looks like a shift by 2 units, and this is just a Laplace transform of t, then we can see that this is actually just, if we take the Laplace inverse of this is just going to be u sub 2 of t times what? Well, the shifted version. Right? Here, this is the Laplace transform of t. Right? So here we need t shifted by 2 units. And that's the whole thing. Right? So working backwards, all you have to do is, can you identify that whatever you're looking at is a product of a shift of a step function and an unshifted function. And then in order to see what the Laplace inverse of that is, well, we know that the Laplace inverse used by theorem 1 is going to be, let me underline, right, the step function that we found corresponding to the shift in the exponential, right? So in the exponential we have minus 2, so the shift is 2. And then here we should have the shifted version of whatever we have here. Right? So this is the Laplace transform of t. We want to shift it 2 units, right? So we get t minus 2. So very simple, as long as you can write it in the right form. Okay? Now, there's one more shifting property that I want to show you, and it's this one. Right? So assume that the Laplace transform of a function f is big F of s, and that it exists for s greater than a greater than or equal to 0. And again, this a comes from the exponential order. Now, if c is a constant, then we can actually calculate the Laplace transform of the exponential with c in the exponent times f of t. And it actually ends up being a shift, not on the domain, but on the range. It ends up being a shift on the big F of s. And what are we shifting by? Well, we're shifting by whatever exponent we have on the exponential. And what's the domain of this new function? Well, it's s greater than a plus c, right, where c is whatever was in the exponent of the exponential. It also goes the other way around. Assuming that f is continuous, we know that the Laplace inverse is going to be unique, right? So in this case, we get the Laplace inverse of big F of s minus c. So big F shifted c units to the right is just e to the ct times f of t, little f of t. So another very nice shifting property. Now let's see an example of this. So find the inverse Laplace transform of f of s equals 3 factorial over s minus 2 to the 4th. Now, if we want to use theorem 2, especially this part, we somehow want to rewrite this function f of s, big F of s, as a shifted function. Okay? So let's take a look at this 3 factorial over s minus 2 to the 4th. This seems to be a shifted version of the function g of s equal to 3 factorial over s minus 2, s to the 4th. Oops. Right, meaning that f of s, which is this original thing, seems to be a shifted version of g of s, being 3 factorial over s to the 4th. Specifically, we have that f of s is equal to g shifted 2 units to the right, 4 units to the right. Sorry, 2 units to the right. I had it right the first time. That's what that looks like. And again, all I did was this analysis. Right? F of s is given by this, and it is very similar to this unshifted function. And then we can just identify explicitly what is the shift. Right? F of s is g shifted 2 units to the right. So now, by definition, the Laplace inverse of f of s is equal to the Laplace inverse of g shifted 2 units to the right, okay, which by definition, looking at theorem 2, is equal to what? Well, it's equal to, so we get the exponential out of it, where the shift has to match this number here. The exponent of the exponential has to match the shift, sorry. So it'd be negative 2t times the Laplace inverse of just g of s. Right? This is what the theorem is telling us. Right? Because this thing here, f of t, is the Laplace inverse of big F of s. Okay? And what is the Laplace inverse of g of s? Well, that looks like, this thing here looks like the Laplace transform of t to the 4th. And in fact, if we go to theorem 1 in section 6.1, you're going to see that in fact, 3 factorial over s to the 4th is the Laplace transform of t to the 4th. Right? So, in conclusion, this ends up being e to the negative 2t. And then here, we know that this is the Laplace transform of t to the 4th. Right? So this is just t to the 4th here. So what is this theorem telling us? Well, first of all, it's giving us a tool, and how to compute the Laplace transform of an exponential times a function f. However, I think more importantly, it's telling us if you ever want to take the Laplace transform of a function of s that looks like a function of s that is shifted, right, whatever units it is, and you know what the Laplace inverse transform of that original function is, right? So in this case, f of s looked like a shifted version of g of s, which we know the Laplace inverse transform. Then you can use this theorem to calculate this Laplace inverse. Right? So basically, you get rid of the shift that happened here by just writing the exponential in front. And then you just have to take the Laplace inverse of the original g of s, which we know how to calculate. So that's the idea. That's how you would use this theorem to calculate Laplace inverse of expressions. Now, finally, in the next video, we're going to apply all this to a more general example. An example of a Laplace of a differential equation, non-homogeneous linear, where our g of x or g of t, whatever the independent variable is a piecewise function.